Thank you, and thank the Mrs. Obermann for the invitation and the opportunity to give a talk. So I will talk about joint work with Erik Habbestad and Lucas Hataishi, PhD students at the University of So the work is motivated by a known old result of Furstenberg, so it talks about by reminding what that result is. By considering Poisson boundaries of random works on groups. So the second is that we'll start with the second countable locally compact group, fix a probability measurement, and then consider left invariant random works. So in other words, Markov operator divided by convolution of function with a measure mu. Then consider bounded harmonic functions, so all functions preserved by this Markov operator. And so from the start, it's just an operator space, but in fact, it's a von Neumann algebra with a new product. So with a new, the product is defined by this formula. So we multiply functions in the usual way, pointwise, and apply power. So this Markov operator led to infinity, and this converges and gives you a new product. And so as a abelian von Neumann algebra, it's just an infinity function from some measure space, and this measure space is called the Poisson boundary of the group. And since our Markov operator is invariant and equivariant with respect to left translations, in fact, this measure space is equipped with an action. So we consider it as a G space. And then the famous result of Furstenberg is the computation of these boundaries for a large class of groups, namely for all connected to semisimple V groups with finite center. And the answer is the following. So we start, we need some minor assumptions on the measure. The following, for example, are enough. So if we fix a maximal compact subgroup in such a group, and we can see the admissible measure, assume also that it's k invariant. So by admissible, I will just mean that it's absolutely continuous with respect to car measure, and it's sufficiently non-degenerate. So a lot of some convolution power of this measure contains the neighborhood of the identity. So in this case, the claim is that this Poisson boundary is just a homogeneous space of this group G, defined by a subgroup which is unique up to conjugacy maximal for compact maximal amenable subgroup of G. And M is just a unique k-invariant probability measure. So I think Furstenberg already suspected that this maximal amenable subgroup is just a minimal parabolic subgroup, but he didn't prove it in full generality, and that was later proved by Moore, that for any such group, this maximal amenable subgroup is exactly the minimal parabolic subgroup. But we will care only about a particular case of this when our group is a complexification of a compact semisimple group. And in this case, this flat manifold, homogeneous space G but P, is just a homogeneous space of K defined by the maximal torus. Okay, so how Furstenberg proved this? So in fact, the large part of the proof is analysis of another boundary, which is a topological boundary, which is nowadays called Furstenberg boundary. And these are defined as follows. He considers a class of actions, which are called boundary actions. They're defined in the following way. So given an action of a group on a compact space, to say that this action is strongly proximal, if we take any probability measure mu, then the orbit of this measure in the closure contains point masses. And if in addition the action is minimal, then this is called a boundary action. And what we show that for any locally compact group, there is a universal boundary action, and corresponding space on which you act is called nowadays Furstenberg boundary. And the proof then goes as follows. So starting from this field, he computed the Furstenberg boundary and showed that it's exactly this space which appeared in the theorem. And then given any G space, you can consider the Poisson integral. So here it's not important what is here, so you could start with any space, and you can consider sort of Poisson transformation, just integrating with respect of the measure, translate it and integrate it. And it's easy to see that you always end up in the harmonic, in the space of harmonic functions, and the main result that this is a complete isomorphism. And it's not so difficult to see, at least under some minor additional assumption, when you that the map is always injective. So the key part is subjectivity and the computation of this space. And so all comes from this analysis of boundary actions. So the main part of the work is really the analysis of boundary actions and computation of Furstenberg boundaries and producing ways of constructing boundary actions and so on. Okay, so that's a classical result back in 1967. But there is some sort of non-commutative analog of this. What was a theory which was started by Masaki Izumo in the late 90s as development of Poisson boundary theory in the non-commutative setting. So you can imitate the same construction which we had in the classical case, so it goes as follows. You could, in principle, do something more general than just random works on quantum groups. The random works on aggregate phenomena algebra, but we'll be interested only in this setting. So we start with a locally compact quantum group. So consider not so important what exactly the definition is. You consider a normal state, and then similarly as in the classical case, we consider convolution operator. And consider the bounded harmonic elements. So elements in L infinity space of G, which is now a non-commutative phenomenon algebra, fixed by this Markov operator. And then again, one can show that this is not just an operator space, this is really a G phenomenon algebra with the product defined in this way. So the product defined in two sense, and then apply powers of your Markov operator, and then you can show that this converges in the outer strong operator topology or something, and this gives you a formula. In fact, we will be interested only in the case, that was the beginning of the theory. People for a long time are interested only in the case of discrete quantum group. So what is a discrete quantum group? It's a dual of a compact quantum group. So L infinite functions on the dual compact group are just the same as phenomenon algebra of a compact quantum group, and as a phenomenon algebra group, it's exactly as phenomenon algebra of a compact group, so it's just L infinity sums of full matrix operators. And here you have certain operators acting on this quite simple phenomenon algebras, and then try to compute this Poisson boundaries. Moreover, you can, from the start, when people try to make life a little bit easier and work with some additional symmetry. So if you are in this setting, you can exploit the adjoint action of a compact group on itself, and consider only states which are invariant under this adjoint factor. And since every representation is irreducible, this means that there is exactly one invariant state with respect to this action. And classically, this is just a normalized trace. If you're in the quantum setting, then this is some state of quantum trace or Q trace, so it's not necessarily a trace. But the point is that all such states are described simply by measures on atoms. We're in the second which is given the discrete set of irreducible classes of irreducible representations. On this set, you have a measure, and out of this measure, you construct a normal state in this phenomenon algebra, and you get certain Markov operator, and then you start with the corresponding Poisson boundary. So that was the second, and then the question: can you actually compute with phenomenon algebras? And that was done in a number of cases, and the cases we're interested are these q-deformations of compact simple Lie groups. So the result was false. So again, you start with a compact connected semisimple Lie group, and then you consider the q-deformation roots. It's again, precise definition is not going to be important. So this is some compact quantum group, and it depends on the choice of a maximal torus. So there is inside this non-quantized maximal torus. It remains sitting in your compact quantum group. And the result as follows already in Hasaki's first paper, where he started this theory. He considers probably the most natural, non-trivial example, namely the case of SU2. And in this case, he showed that the Poisson boundary for any generating probability measure is exactly this flat manifold. So quantum flat manifold, the deformation of a two-dimensional sphere. And then, together with Masaki and Mark-Chusset, we proved that the same is true for SUM, for arbitrary M. And we actually proved some partial results for all types of the subjectivity of Poisson integrals to the full generality. So at this point, it was clear that the answer would be the same as in the classical case, in the flat manifold. And soon afterwards, it was indeed proved by Tomatsu, and he actually proved a much more general result, which I will return to. And by now, there is also a somewhat different proof of this result due to Yamashita and myself, but this will play an important role later, so I will return to this. So when you look at this, it's clear that this is related to the result of Furstenberg, right? I mean, we're dealing with random verbs on groups or quantum groups, and the result would be the same. We get flat manifold in the classical case and quantum flat manifold in the quantum case. So certainly this is no coincidence, but somehow the conceptual understanding of this was missing. And for example, one of the things was that in the classical case, we're considering Poisson boundaries of non-discrete groups. And actually, non-discreteness is quite important. For example, if you try to compute the Furstenberg boundary, it's not known for any discrete group, but you can actually compute it in a non-discrete case. But here we're dealing with these discrete ones, these discrete rules. But also, when we kind of naively pass to the classical limit, then there is no connection really between these results. So it's very important that this deformation parameter here is not equal to 1. So we are really not in the classical case. If you just let q equal 1, then the Poisson boundary of the dual of any compact group is trivial. That was proved by Jan in the Poisson one time ago. This is what he called noncommutative Shekelini theorem. So somehow things are similar, but it remains a bit unclear how they are related. And back then, that was quite old result. I think our result is like from 2004, 2005, and in Tomatsu is from 2006. So I spent some time trying to understand what the connections are between the settings and the approaches in computing, but he didn't have any good idea. But now there's some new incentive to look at this because of appearance of non-commutative Furstenberg boundary theory. So let me say a few words about this. But before we do this, let me give some sort of conceptual explanation why the results are still somewhat similar. So the reason is that it turned out that this is not a difficult result, but it really kind of puts things in the right perspective. So it turns out that while we considered random works on discrete quantum groups, in fact, it's more correct to view this as random works on non-discrete ones. And for any compact quantum group, you can consider its Greenfield double. And as a phenomenon algebra, it's just an L-infinity function for phenomenon algebra on discrete group, and L-infinity functions on the group itself, but it has some complicated properties that it's not important how to exactly define it. And this is known that this quantum group, in the case of q-deformations of semisimple Lie group, should be considered a sort of quantum analog of the complexification of a compact group. That was, but one should understand in which sense, right? In the sense of the Poisson Lie groups, that this is explained already by Greenfield in the 80s, but from the analytical point of view, this is not so straightforward to see. So from kind of representation theoretic point of view, that was analyzed by Push, Voronovich, and but to really see that you kind of have deformation of this classical group into these quantum groups. For example, if you want a continuous field system algebra, this is quite difficult, and that was done only recently by the Comer and Montfort. Anyway, so one knows that by now that this is really a good replacement of the complexification of a group. But classically, it doesn't really work. So if you're really in the classical setting, then this is the algebra of the Greenfield double, just this is the algebra, and not this is the algebra of the complexification. That's why you have to be careful when you pass to the classical limit with some theory. Anyway, so the claim is then the following: that if you start for any compact quantum group and you start with these probability measures, then there is a canonical decay equivariant isomorphism between the Poisson boundary of the discrete group and the Poisson boundary of this Greenfield double with respect to certain measure. And so, in fact, even though we sort of consider random verbs on discrete groups, it's we can view them as discrete as random verbs on non-discrete ones. And from this point of view, then it's quite natural that the numbers are the answers are zero, and you get 4 faults in both cases. But then you can really ask, so what is the connection between the approach of Furstenberg and the approaches which we use to compute the Poisson boundaries in the quantum space, and this is appearance of Furstenberg boundary theory, non-commutative Furstenberg boundary theory. The hope was, and that was one of the motivations of this paper, is that maybe we can then develop some Furstenberg boundary theory for Greenfield doubles, and then use already non-computations of Poisson boundaries to compute Furstenberg boundaries of such things. That's kind of the goal. But first, let me say a few words about how one views Furstenberg boundary theory from operator algebraic point of view. So recall that we have the notion of injectivity for system algebra. So if we consider G system algebra, then we call G injective if it's G injective object in this category with UCP maps, roughly speaking. So in other words, if you have UCP map, equivariant UCP map from B to A, and you have a complete isometric embedding of B into C, then this map can be lifted to a G equivariant UCP map from C to A. And then result of Kennedy, which was in fact observed by Hamana a long time ago, but did not have much attention, but it was rediscovered recently by and Kennedy, that if you say in the discrete group setting, then the algebra of functions on the Furstenberg boundary of a group is the injective envelope, object on this number. So in other words, this algebra is G injective, and moreover it has this additional property that every G equivariant UCP map into any other G algebra, G system algebra is completely isometric. So this notion then you can use in various non-commutative contexts, and this led to various versions of Furstenberg boundary theories. I think the first paper was by Boris, developed Furstenberg boundary theory for groupoid system algebras, and was used by Bevan and Kalantar in representation theory, and then there are a number of other papers, and maybe particularly relevant for this talk is work of Kalantar, Kasper, who develops Furstenberg boundary theory for discrete form. So, if we know this, the goal then is to develop Furstenberg boundary theory in this work, maybe not for general locally compact quantum group, but at least for Greenfield doubles, and then compare the result of Furstenberg with computations of Poisson boundary, say something about this Furstenberg boundary. But in fact, at this point, I'm going to abandon quantum groups and formulate everything in terms of categories, which I think maybe will make some people even less happy, but hopefully some people will be more satisfied with tensor categories rather than properties. And I explained that what's to by now there is kind of understanding that these are more or less equivalent settings. So needn't achieve much by doing this, no rule set of so I will do it in the setting of C-star tensor categories. So for this we need to understand like in which category we're working with. Like in this setting we're working with the G C-star algebra. So C-star algebra is equipped with action of a group, right? And we can see the completely positive maps and completely isometric maps between equivariant maps between this algebra. In the categorical case, we have to understand what the setting are and what the right maps are. So, and the setting will be the following. So consider a fixed C-star tensor category. So in the quantum group setting, this is like a representation category of a compact quantum group, but we can consider more generally C-star tensor category. And with the following definition, we will say that another C-star tensor category is a C tensor category if it is equipped with a dominant unitary tensor functor from C in the without lots of generality, we can actually assume that C is simply a C-star tensor subcategory of B. And so the assumption is that, in other words, that the objects in C are kind of enough to generate the entire category of B. So what you do, in B you can have more morphisms than in C. And so this will be our category, which is replacement of the category of G C-star algebras, and then we need completely positive and completely isometric maps, and those are already, these complete positive maps are already known. So there are some papers on various aspects of this thing. So I think maybe one of the first, or maybe the first categorification of completely positive map was in the paper myself with Makoto, where I can see that the categorical versions of invariant means. And there was a paper by Popper and Stefan, where we can see that called multipliers of C-star tensor categories, and then it was considered by Corey Jones and David Dennis defined completely positive pairs for modular categories. So all in all, the following definition is known, and this is actually exactly the setting of Corey and David. But in the case of bimodular category, so we sort of view this category B as a bimodular category. And then this is actually the definition they had, but we'll use slightly different name. I kind of don't like the name multiplier because multiplier, I think it suggests that it's a map on the same category, where there's between different ones should be something different. So let's call it a C-linear transformation between two such tensor categories. So what it is? It's a natural transformation between these bifunctors of taking morphisms. So in other words, this is a collection of maps between morphism spaces in the first category and morphism spaces in the second category, which is natural with respect to morphism in C, and which have this sort of mild property of respecting sort of tensor properties. So we're not requiring this theta to be like multiplicative of tensors, but you only require this small property. And declaring this does the right thing. So using this, you can then introduce the notions of complete positivity, complete isometry, complete boundedness, and so on. So maybe we consider such linear transformation completely positive if all such maps are completely positive and so on. Complete isometry, complete isometry, and so on. And this gives you the right thing. So by the following result. So the first part explains, as I said, why you don't really lose anything by going to categories instead of working with sister algebras. And it turns out that if you start with a compact quantum group, then rep K tensor categories, in the sense I introduced. So they form a category. This category is equivalent to the category of sister algebras with an action of the Greenfield double, but actually as a plus of it, which is braided community of sister algebras. So this is related to what Hans talked about. So it's a well-known result of Hausdorff that modular categories correspond to algebra objects in your category, and in this setting, sister algebraic setting, a similar result is that modular categories over rep K correspond to K sister algebras. But then for modular categories, one can ask, okay, what if my modular category is in addition a tensor category, and the action is given by a tensor function? And so the result says that this happens if and only if, in addition to, you don't have just an action of K, you actually have an action of the Greenfield double, and you have sort of braided commutativity. So, and this result allows you to go back and forth between the setting of sister tensor categories and the setting of its braided commutative DK sister algebras. And the claim that under this correspondence, all these definitions, they give you the right thing. So that the notions which we introduced for complete positivity, complete isometry, and so on, they exactly transfer the usual notion of complete isometry, complete positivity, complete boundedness for sister algebras with reduction of DK. And moreover, say the completely bounded norms, they really negative. This is the one the result of some value in the second part, because in one direction it's not difficult to see that you have categorical maps dominated by sister algebraic maps, no, but in the opposite direction it requires a little bit of work. Anyway, so this just justifies this definition. So it captures the right properties, and then we can just imitate the approaches of Hamana and all subsequent works describing, defining non-commutative Furstenberg boundaries in different contexts. So then we can say that a C tensor category A is C-injective. It has exactly this injectivity property, so that as soon as you have another C tensor category and a completely positive transformation between them, and you have a complete isometry between this C tensor category and this one, then you can construct complete isometry making the diagram commutative. Commutative means that you just have commutativity for all pairs of objects. And then we can say that a C tensor category A is called Furstenberg-Hamana boundary of C if it is injective in this sense. And it has this property that if you have any completely positive map from it into another C tensor category, then it is completely isometric. And the question is why such a thing exists? And the argument goes along sort of over standard out lines. So the claim is that for any small rigid sister tensor category with simple unit, there is a unique equivalence Furstenberg-Hamana boundary. And the rough sketch is as follows. So first, that's the key step in every such generalization of Furstenberg boundary theory. You first have to see that there at least exist enough injective objects. And so we need to come up with at least one injective object in this case. In this case, this is the category C hat. So what is it? You can consider category C as sitting inside category of end functors of C when C acts on the left, on the right side. And then consider the category generated. So the objects are the same, but there are morphisms. There are many more morphisms. So and the claim is that this is an injective object, and the way to think of it is this is an analog of a function algebra on a group. So this is a result of the form that if you can say it's a finite group, then if you consider function algebra with a graph function by translation, then this is an injective G model. So the claim is that this category is C-injective in the sense we introduced, and more precisely why it is the case, because it is easy to describe, or it's possible to describe all completely positive maps into this category, namely all such completely positive maps are in a one-to-one correspondence with just states on the endomorphism ring of the unit. So, and because you can extend states, of course, from a sister algebra to a larger sister algebra, this gives you this injectivity. So once you have this, the rest is already completely standard. Then you can so you embed already a category that's something injective. But then inside of this large injective object, you have to find sort of minimal one. So you consider the compact constant semigroup of all such C-linear DCP transformations on this category. Then, because of this compactness and convexity, it has a minimal idempotent, and this minimal idempotent has this property, and this is what this goes back to Hamana. And once you have this idempotent, then you can define new categories. So you start with this category C hat, but then you consider a smaller class of morphisms. So instead of all possible morphisms in this C hat, we consider only morphisms which are fixed by this idempotent. And again, this will start just some operator spaces, but we can introduce a new composition using Schoenberg for product. So we multiply and then project down the space, and this gives you a result. Okay, so we have this Furstenberg boundary for any C that the category, and for the same reason or similar reason, we have Furstenberg boundary for all these Greenfield doubles. Now the question how it compares to Poisson boundaries. And for Poisson boundaries, there is a categorical notion which was introduced by Makoto and myself some years ago, and I will not introduce it. In complete generality, I will rather formulate an important property of this object, which allows you to compare it in some cases to Furstenberg boundary. And you should not expect that there is a general comparison. So usually, in the classical theory, these are different spaces. Furstenberg boundary is so it's topological space, not separable and so on, and while Poisson boundary in general just a measure space. So there is no kind of direct way of comparing, but sometimes you can compare that. And in the categorical case, I will introduce this Poisson boundary only in this particular case where we know how to compare things. So to describe this, let me rewind the notion of amenability in the categorical sense. So there is a notion defined in terms of a just-in-time condition of amenability. So how they define? So we consider our rigid sister tensor category C. We consider representatives of simple objects, and then we have this sort of fusion matrices which describe the tensoring of simple object by a given object Q. And then given a dimension function on this category, one says that this dimension function is amenable if the norm of this matrix is exactly the dimension of this object. So definition in various particular cases goes back to Pope and then Wanda Roberts, but then formalized by using here. And an equivalent condition is to say that in this L2 space over the set of representatives of simple objects, you have almost invariant vectors with respect to these matrices or preciseness and normalization of the matrices. But what is nice and important that it turns out that in this quantum or categorical second, not all possible sort of definitions of amenability agree. So another definition classically is, of course, just maybe two main definitions. One is to say that a group is amenable if there is an invariant mean, Another one is to say that you have almost invariant vectors in it. It turns out that in this case, these are not equivalent conditions. So this condition is strictly weaker if it requires existence of an invariant mean, or equivalently you can say that there exist almost invariant non-negative vectors to expected as properly normalized matrices in A1 space. And for groups, these are of course the same thing, but for categories, it's not. And this will play an important role. Okay, if we're recalling this, I can inform a way definition and, but not so much definition, but the main property of the Poisson boundary, which Makoto and I proved. Well, we needed some minor restrictions on the category, so this was Erik and we just remove those restrictions. So, but the main part anyway, our operator with Makoto. So the claim is the following. So supposing in this setting that you have a small rigid system and the category with simple unit and weakly amenable intrinsic dimension function. So, amenable but only in a weak sense. And the claim is that there exists a unique auto-equivalence C tensor category with simple units still, which we call the Poisson boundary of C, satisfying the following condition. So the first is that this category sort of minimizes the dimension function all the way to the norm of the matrices. So the point is that amenability is the requirement of equality, but what we always have is an inequality, that the norm of the matrix is not larger than the dimension function. So, so what can happen is that you can, even if you have inequality, you can embed the category into a larger category where you can have more morphisms, so more ways of solving conjugate equation, and in that larger category, the norm of the matrix can be equal exactly the dimension. And the claim is that this Poisson boundary does exactly that. So it minimizes the dimension function to the lowest possible minimum, exactly the norm of all those fusion matrices. And it has this universality property that it is sort of the initial object among all such things which do this minimization. So if you have another C tensor category with simple unit and the same property that it minimizes the dimension function all the way to its lowest possible minimum, then you can actually have an embedding of the Poisson boundary in this one. So why this called the Poisson boundary? Because it's constructed. I don't give a definition, but it's constructed as sort of Poisson type boundary. More precisely, the way it appears is that again you can see this category C hat, which I considered before, and then you have to consider much smaller class of morphism, namely you consider morphism which are invariant and all for some transformations in your category. And that's why it's called Poisson boundary. It sort of consists of harmonic morphisms. Well, but why I'm not giving the precise definition? Because in this form, if you just give the definition, then again always a question how do you compute such things? And this universality property actually allows you to compute it without knowing what the actual definition is. So one of the main examples related to the result of some answer I mentioned earlier is the following. If you start with any compact quantum group, which is called co-amenable, in other words, it's dual of an amenable discrete quantum group, then using this universality, you very quickly see that the Poisson boundary of this representation category will be another representation category where this H is the so-called largest closed quantum subgroup of cut stars. This quantum subgroup is the antipode square spread. And this allows you to compute those things in many cases. Okay, so having done this, now we can formulate one of the main results. So the claim is that in the setting of the previous theorem, these things actually agree. So that if you have any small rigid system tensor category with simple unit and weakly amenable intrinsic dimension function, this is something where we can compare this, then this Furstenberg boundary and Poisson boundary are equivalent. And this is what I want to suggest or want to look at as this categorical analog result of Furstenberg, which describes the Furstenberg boundary as a quotient of homogeneous space with respect to the maximal and minimal cycle. So this Poisson boundary is defined in terms of some maximality or minimality of some amenability, and so it's kind of in the spirit of similar result. So how this related to things we started with? Before doing this, let me just mention that out of this you can prove some basic properties of some Furstenberg boundary. For example, you can compute exactly, as in the case of discrete groups, that the Furstenberg boundary is trivial. In other words, you are not going to get any new category, even only if the category you started with is already amenable. In other words, the intrinsic dimension function is amenable rather than weak. In other words, what Furstenberg or Poisson boundaries measure in this case is this sort of discrepancy between weakly amenable case and amenable case. And another consequence is that it sort of shows that maybe this is the only setting where you can hope to have any complete understanding of Furstenberg boundary. So, as I already mentioned, if you start with a non-amenable discrete group, then one doesn't know a single group for which one has a good description. The Furstenberg boundary is some universal huge construction. And sometimes, I think sometimes this happens in this case as well, but so precisely what we can say is that this new category, it has simple units, even only if this category we started with has weakly amenable intrinsic dimension. So as soon as we're not in this weakly amenable setting, the units will be already some C-standard, probably non-separable, and already correct. The endomorphism of the unit are probably already impossible to describe in an explicit way. So I think this was the best you can hope. Okay, but returning to the cases we started with, then we can use now. So if Furstenberg work here used Furstenberg boundary to compute Poisson boundary, now using the Poisson boundary we can actually, and this result we can actually compute Furstenberg boundary. So we can say the following, that if you, this is related to that example, the result of Tommaso, that if we start any compact quantum group which is co-amenable, do an amenable quantum group, then the Poisson boundary and the Furstenberg boundary, so I should put that in the Furstenberg boundary, is exactly this representation category where H is the largest quantum subgroup of Katz type. And in the particular case, if you have a compact connected semisimple Lie group with a fixed maximal torus, then the Furstenberg-Hamana boundary of the representation category of the q-deformation is exactly the representation category of the maximal torus. And this is really quantum analog, categorical analog of the result of Furstenberg and Moore, but the Poisson boundary is exactly the algebra functions on the flat manifold. Yeah, in principle, this result can be used in some other cases. Let me just mention one more case, which will be closer to thoughts of some people here. But again, it's not really new. It's an example from our paper with Makoto, where we identify Poisson boundaries, but how we can say that we interpret this result also as a computation of Furstenberg-Hamana boundary. So if you start with a 2-1 factor, and you take an extreme of finite index subfactor, then consider the corresponding system anti-category. So we consider a category of n bimodules generated in this algebra object n. And let us consider the standard model of this subfactor, which is a tunnel that goes the union of relative commutants. And assuming that this standard model, so we make two assumptions, that first of all, the subfactor is extremal, and the second is that the standard model and is a factor, and the Furstenberg-Hamana boundary of this category is exactly the category defined by this factor-subfactor pair, so the standard model. So in this case, the computation of this Furstenberg boundary is the passage from the original factor-subfactor to its standard model. Okay.